Where are we truly located? Not just your house number, nor the name of your street. Not merely your town, city, or even your country on a continent of Earth. But where is Earth, really? It resides in the solar system, nestled between Venus and Mars. A familiar enough answer. Yet this solar system is more than just its planets. It's a dynamic hub of activity, dominated by the Sun's gravitational influence, extending outward into the enigmatic Oort cloud, a vast, spherical shell of icy objects and ancient comets marking the Sun's cosmic reach. Still, the Oort cloud is but a minor structure within the local interstellar cloud, a faint mist of gas and dust that itself swims within the local cavity, an expanse of relatively low-density space carved out by ancient supernovae. This local cavity is part of the Orion arm of the Milky Way, a galaxy defined by its magnificent, spiraling arms of stars and cosmic dust, all circling a supermassive black hole cloaked in mystery at its galactic core. The Milky Way spans more than 100,000 light-years, a staggering size on human terms, yet in the cosmic context, it is but a fragment. As we zoom outward, the local group emerges, a collection of 30 to 50 galaxies bonded together by gravity. Among them is Andromeda, a galactic titan twice the size of the Milky Way, hurtling toward us on an inevitable collision course. In a few billion years, these galaxies will collide, their stars pulled and scattered before settling into a new, merged form. But even this cosmic drama is a mere footnote at greater scales. The local group is part of the Virgo supercluster, a sprawling congregation of thousands of galaxies. Yet Virgo itself is dwarfed by the Laniakea supercluster, a monumental structure hundreds of millions of light-years across. Within Laniakea, filaments of galaxies connect like threads in a vast cosmic web, weaving through voids such as the Boötes Void, a chilling expanse 330 million light-years across that holds fewer than 60 known galaxies, a near emptiness in the fabric of existence. As we continue to zoom out, we reach the edge of the observable universe. Here, light has journeyed to us for 13.8 billion years, carrying whispers from the dawn of time. However, the universe's expansion means that the true edge lies much farther, 46 billion light-years away in every direction, forming a sphere 93 billion light-years in diameter. Beyond this boundary lies the unknown. At scales this vast, the observable universe itself becomes a map of grand structure. Galaxies cluster into groups, which in turn form superclusters and filaments. Yet even within this magnificent order, scientists encounter what they term the end of greatness, a conceptual limit to cosmic structures that defies further hierarchy. It begs the question, why is the universe so structured? How did a primordial soup of particles evolve into this stunning array of stars, galaxies, and voids? Was this order inevitable, or is it the result of some profound cosmic symmetry? Even more importantly, how do we know? Mapping the cosmos. The story begins in 1502 with Nicholas Copernicus, a young polymath meant to be studying medicine in Padua, Europe's center for healing. Yet his mind was not confined to earthly ailments. By night, he pored over the works of Aristotle, Plato, and Ptolemy, finding inconsistencies in the prevailing geocentric models of the cosmos. A decade later, in quiet defiance of convention, he drafted his revolutionary theory: Earth is not the center of the universe. We are but one planet orbiting the Sun, unexceptional in a vast cosmic dance. Copernicus delayed publishing his ideas for fear of the upheaval they would cause. It wasn't until his 70s, some say on his deathbed, that his seminal work finally emerged, shaking the foundations of science, philosophy, and religion. The Copernican principle, as it is now known, declares that Earth holds no privileged position in the cosmos. This seemingly humbling revelation opened the door to boundless exploration. If we're not special, what else might be out there? Modern cosmology rests on this principle, supported by discoveries like the cosmic microwave background radiation. This faint, primordial glow permeates the universe, no matter where you look. Discovered in the mid-20th century, the CMBR is a relic of the early universe, emitted when matter cooled enough for light to travel freely for the first time. Its uniformity, 2.7 Kelvin across all directions, suggests that, on large scales, the cosmos is homogeneous. Yet here lies a paradox. Our local cosmic neighborhood teems with structure, galaxies, clusters, and superclusters connected by filaments of matter, interspersed with vast voids of near-nothingness. How can the universe be both uniform and filled with such intricate patterns? The answer lies in the interplay of two opposing forces, expansion and gravity. Shortly after the Big Bang, the universe underwent a period of rapid inflation, stretching any initial irregularities across vast distances. As expansion slowed, gravity began to dominate, causing denser regions to pull in surrounding matter. These overdensities grew, forming stars, galaxies, and eventually the vast cosmic web we observe today. But where did these initial fluctuations come from? The first hints emerged in 1989 with NASA's Cosmic Background Explorer. COBE provided the first baby picture of the universe, mapping tiny variations, anisotropies, in the CMBR. These were incredibly subtle, 1 part in 100,000, but they marked the seeds of cosmic structure. This groundbreaking discovery inspired successive missions, each sharpening our view. The Wilkinson Microwave Anisotropy Probe in 2001 and the European Space Agency's Planck satellite in 2009 revealed increasingly fine details of these early fluctuations. Together, they confirmed that tiny quantum irregularities, stretched by inflation and sculpted by gravity, gave rise to the galaxies and clusters we see today. On Earth, telescopes like the Sloan Digital Sky Survey have taken mapping to new heights. Nestled in New Mexico, SDSS collects light from thousands of celestial objects simultaneously, using custom-drilled aluminum plates and fiber optics to measure their distances and motions. This meticulous work has revealed structures like the Laniakea supercluster, our galactic home, and the Sloan Great Wall, a billion light-year expanse of galaxies. But even these colossal structures pale in comparison to recent discoveries. In 2021, astronomers identified the Giant Arc, a structure spanning 3.1 billion light-years, so vast it challenges our assumptions about cosmic uniformity. At this scale, the universe appears as a vast network, filaments of matter connecting clusters, with dark voids stretching between them. This raises a surprising question. What is the nature of this cosmic web? Is it like a soup of meatballs floating in empty space? Or is it more like a honeycomb or sponge, with dense regions separated by voids? Cosmologists have debated these metaphors for decades, not for their whimsy but for their profound implications about the underlying physics of the universe. The truth, as always, lies in the data. By combining observations from ground-based telescopes, space missions, and advanced simulations, scientists are gradually revealing the grand architecture of the cosmos. It is a structure born from chaos, shaped by forces we are only beginning to understand, and filled with patterns that echo across billions of years. And as we continue to map the universe, we may yet uncover deeper truths about its nature and our place within it. As we push the boundaries of our understanding, each discovery leads to new questions. The universe, with its vast structures, appears to follow certain rules, but the full extent of its organization remains elusive. The cosmic web, a network of galaxies, clusters, and voids, suggests a pattern, but what determines its shape? Is the universe governed by simplicity or complexity? The largest structures we see today are a result of billions of years of cosmic evolution. Fluctuations in the early universe grew into galaxies and clusters, but why did those fluctuations exist in the first place? These irregularities are thought to be quantum in origin, tiny uncertainties amplified during inflation. Yet this explanation leaves room for deeper mysteries. What drove inflation? What is the true nature of dark energy, which now accelerates the universe's expansion? One tantalizing idea is that the universe's structure may reflect the geometry of spacetime itself. Einstein's theory of general relativity showed that gravity isn't merely a force but the warping of spacetime by mass and energy. On cosmic scales, this warping creates the scaffolding for the web-like structures we observe. Dark matter, though invisible, acts as the glue that binds galaxies together, while dark energy stretches spacetime apart. Together, they shape the universe into a delicate balance of connection and isolation. And yet, even this balance raises profound questions. Recent discoveries, like the giant arc and the KBC void, a proposed supervoid nearly 2 billion light-years across, challenge our assumptions about the universe's uniformity. Are these anomalies rare exceptions, or do they hint at something deeper about the fabric of reality? Mathematically, the universe's structure invites comparisons to familiar patterns, a sponge, a honeycomb, or a soup. But the true answer may be stranger than any metaphor. The interplay between cosmic forces, gravity, expansion, and the unknown drivers of dark energy and dark matter creates a complexity that defies simple explanation. This complexity is both humbling and inspiring. It reminds us that our understanding of the cosmos is still in its infancy. We have mapped only a fraction of what exists, and the tools at our disposal are improving with each passing decade. Telescopes like the upcoming James Webb Space Telescope and observatories such as the Vera Rubin Observatory promise to unlock new realms of knowledge, from the earliest galaxies to the nature of dark matter. In this grand effort to map the cosmos, we are not just charting stars and galaxies, we are seeking to understand the origins of everything, including ourselves. Every map, every image, and every spectrum collected tells a story about where we come from and where we might be headed. The structure of the universe. In the mid-20th century, as the Cold War raged, two competing schools of thought emerged on opposite sides of the Iron Curtain. In Princeton, New Jersey, a mild-mannered Canadian physicist named Jim Peebles pondered how tiny fluctuations in the early universe could grow into galaxies and clusters. His theory imagined the universe as a meatball soup, matter clumped together by gravity into roughly spherical regions, leaving vast, low-density voids. This bottom-up model suggested that small structures merged to form larger ones, eventually building the cosmic web we see today. Meanwhile, in Moscow, Yakov Zeldovich, a veteran of the Soviet atomic program, was thinking along different lines. Zeldovich envisioned the universe as a series of two-dimensional pancakes of matter. According to his top-down theory, these large-scale structures formed first, with galaxies emerging where the pancakes overlapped, creating filaments and clusters. Between these filaments lay vast voids, shaping the universe into a series of interconnected planes. The two models, meatballs versus pancakes, reflected not just scientific preferences but also the contrasting intellectual cultures of their creators. Zeldovich, constrained by Cold War politics, rarely traveled outside the USSR, so his ideas spread more slowly than Peebles'. In contrast, Peebles' theories gained traction in the West, bolstered by a growing body of observational evidence. But neither theory fully captured the universe's complexity. A new perspective emerged through an unlikely intermediary, Martin Rees, a British astronomer who acted as a bridge between the American and Soviet schools. Rees's postdoctoral researcher, Richard Gott, met Zeldovich at a 1977 conference in Estonia, where they exchanged ideas that would lead to a third, hybrid model. Inspired by both schools, Gott proposed that the universe resembles a sponge, a structure neither entirely clumpy nor flat. In this model, high-density and low-density regions are complementary, connected in a way that balances the competing forces of gravity and expansion. The sponge-like topology suggested that matter and voids were intricately linked, creating a universe that was both complex and self-similar at different scales. As telescopes improved and surveys like the Sloan Digital Sky Survey mapped the cosmos in unprecedented detail, Gott's sponge model found strong support. Observations revealed filaments of galaxies weaving through vast voids, forming a cosmic web. Neither the isolated clumps of Peebles meatballs nor the flat sheets of Zeldovich's pancakes fully captured this intricate network. Instead, the sponge-like structure provided a more accurate description of the universe's vast, interconnected architecture. Yet, even as these maps revealed the grandeur of the cosmic web, they also uncovered something unexpected, a phenomenon scientists call the end of greatness. Beyond scales of about 1 billion light-years, the universe appears homogeneous and isotropic, the same in all directions. The intricate structures of galaxies, clusters, and filaments give way to a smooth, uniform expanse. This transition raises profound questions. Why does structure vanish at this scale? Why does the universe become so unstructured, so featureless, beyond a certain point? The answer lies in the interplay of cosmic forces. On small and medium scales, gravity dominates, pulling matter together to form the structures we observe. But on the largest scales, the universe's expansion, driven by dark energy, becomes the defining force. The acceleration caused by dark energy stretches spacetime itself, smoothing out irregularities and erasing the clumps and filaments that define smaller scales. This shift reflects a fundamental aspect of the universe. While local regions are shaped by gravity, the cosmos as a whole is governed by the principles of relativity and thermodynamics. The universe's homogeneity at large scales aligns with the cosmological principle, which states that the universe is uniform when viewed from a sufficiently broad perspective. The end of greatness serves as a humbling reminder of the balance between order and chaos. On one hand, gravity creates intricate patterns, weaving galaxies and filaments into a grand cosmic web. On the other, dark energy works to erase these structures, pulling the universe toward an ultimate simplicity. The universe, in its sponge-like complexity and eventual uniformity, invites us to look beyond simple metaphors and toward the profound interplay of forces that shape everything we see. It is a story of contrasts, of gravity and expansion, structure and smoothness, and the ongoing quest to understand a cosmos that defies our imagination. Imagine standing on the equator in Ecuador, gazing up at the night sky with a powerful telescope. You carefully measure the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Now, imagine flying to Indonesia, on the opposite side of the Earth, and making the same measurement. Astonishingly, the temperatures match to an extraordinary degree of precision, differing by no more than 1 part in 100,000. Yet these regions of the universe are now separated by tens of billions of light-years, far too distant to have ever communicated through the exchange of light or heat in the 13.8 billion years since the Big Bang. How, then, could they have arrived at such a precise agreement in temperature? This conundrum is known as the horizon problem, one of the most profound challenges in cosmology. The extreme uniformity of the CMBR, while essential to our understanding of the universe, defies the basic principles of thermodynamics. It suggests that regions of space separated by vast distances must have once been close enough to interact. The solution to this mystery lies in a radical idea, inflation, a theory first proposed by physicist Alan Guth in the 1980s. Inflation posits that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space itself grew so rapidly that regions once in close contact were flung apart faster than the speed of light. This does not violate the cosmic speed limit, as it is space itself, not objects within space, that expanded. Through inflation, the horizon problem vanishes. The regions you observe from Ecuador and Indonesia were once so close that their temperatures could equalize. Then inflation stretched these regions to immense distances, locking in their uniformity and creating the seemingly homogeneous universe we observe today. But inflation does more than solve the horizon problem. It explains why the universe is flat, a property confirmed through precise measurements. Flatness, in this context, refers not to a lack of dimensions but to the universe's geometry. In a flat universe, parallel lines never converge, and the angles of a triangle always add up to 180 degrees. Observations of the universe's density, coupled with measurements of the CMBR, strongly support this flat geometry, a hallmark prediction of inflation. Inflation also provides a framework for understanding the small imperfections in the CMBR, the seeds of the universe's large-scale structure. These slight variations in temperature, amplified during inflation, correspond to tiny differences in density. As the universe expanded and cooled, gravity acted on these density fluctuations, pulling matter together to form stars, galaxies, and cosmic filaments. But where did these primordial fluctuations come from? To answer that, we must consider the strange and noisy nature of quantum fields. Even in a vacuum, emptied of all matter, cooled to absolute zero, and shielded from radiation, quantum fields persist. They fluctuate randomly, creating tiny variations in energy. These quantum fluctuations, magnified by inflation, became the first cosmic seeds, the precursors to the structures we see today. After inflation, the universe continued to expand and cool. Around 380,000 years after the Big Bang, it reached a critical threshold. Protons captured electrons, forming neutral hydrogen atoms. This decoupling of matter and light allowed photons to travel freely, creating the CMBR. But the story of structure building was far from over. As the universe cooled further, baryon acoustic oscillations, sound waves rippling through the primordial plasma, left an indelible imprint on the distribution of galaxies. These waves, driven by the interplay of gravity and photon pressure, froze into place when the universe became transparent, leaving characteristic patterns in the clustering of galaxies at a scale of 150 megaparsecs. Yet the true architect of the cosmic web was not ordinary matter but dark matter, an enigmatic substance that outweighs regular matter by a factor of 5. Dark matter interacts primarily through gravity, forming the invisible scaffolding upon which galaxies and clusters are built. While ordinary matter responded to photon pressure and formed BAOs, dark matter remained unaffected, anchoring the densest regions of the universe. The existence of dark matter was first hinted at in the 1930s by Fritz Zwicky, who noticed discrepancies in galaxy cluster masses. Decades later, Vera Rubin's observations of spiral galaxies confirmed its pervasive influence. Stars at the edges of galaxies moved faster than expected, revealing the presence of a massive, unseen halo of dark matter. Today, dark matter is central to our understanding of cosmic structure, yet its true nature remains elusive. The leading hypothesis posits the existence of WIMPs, but direct detection efforts have yet to yield conclusive results. Despite this, the gravitational effects of dark matter are undeniable. It shapes galaxies, drives gravitational lensing, and determines the universe's large-scale structure. Through the interplay of quantum fluctuations, inflation, dark matter, and baryonic processes, the universe grew from an almost featureless expanse into the intricate cosmic web we see today. From tiny seeds to galaxy-spanning filaments, each stage of the universe's evolution tells a story of balance between chaos and order. And yet, mysteries remain. What is dark matter? What sparked inflation? What lies beyond the observable universe? The quest to answer these questions continues, reminding us that while we have come far in mapping the cosmos, we are still at the dawn of understanding its deepest truths. The story of the universe, while awe-inspiring in its detail and depth, is far from complete. For all that we have uncovered, quantum fluctuations as cosmic seeds, the epoch of inflation, the scaffolding of dark matter, and the baryonic ripples that shaped galaxy clustering, there remain profound mysteries at the heart of cosmology. One of the most pressing questions is the nature of dark energy, the force driving the accelerated expansion of the universe. While dark matter serves as the invisible architect of the universe's structure, dark energy plays the role of a disruptive force, pulling galaxies apart and ensuring that the cosmic web thins over time. What is it? A property of spacetime itself? A new quantum field? Or something entirely beyond our current understanding? This accelerated expansion also raises questions about the ultimate fate of the universe. If dark energy continues to dominate, will the cosmos end in a big freeze, with galaxies drifting so far apart that the night sky becomes dark and desolate? Alternatively, could dark energy reverse its behavior, leading to a big crunch, where the universe collapses back into a singularity? Some theories even suggest a cyclical universe, where each Big Bang is followed by a big crunch in an eternal cycle of creation and destruction. Another enigma is the asymmetry of matter and antimatter. The early universe likely produced equal amounts of both, yet today, matter overwhelmingly dominates. What mechanism caused this imbalance? Experiments like those conducted at CERN aim to uncover the fundamental processes that tip the cosmic scales, allowing galaxies, stars, and life itself to emerge. Moreover, while the observable universe has been mapped with increasing precision, it is but a fraction of the whole. The universe beyond our observable horizon is shrouded in mystery, possibly holding clues to the fundamental nature of reality. Are there infinite copies of our observable universe, as some interpretations of inflation suggest? Or does the cosmos end abruptly, beyond which lies an unknowable void? Then there is the tantalizing possibility of multiverses. If inflation can occur once, could it occur multiple times, spawning an ensemble of universes with different physical constants and laws? If so, how did our universe end up with the precise conditions necessary for stars, galaxies, and life to form? This question touches on the anthropic principle, a philosophical consideration that the universe's properties must allow for observers like us to exist. Even the structure we see today, magnificent as it is, may conceal deeper truths. The cosmic web, with its filaments and voids, reflects the interplay of forces in a universe of 4 dimensions. But what if there are higher dimensions influencing this structure? String theory and related frameworks suggest the existence of extra-spatial dimensions that could subtly shape the universe's evolution. Finally, there is the question of time itself. What came before the Big Bang? Did time have a beginning, or is it an emergent property of the universe's laws? These are questions that stretch the boundaries of both science and philosophy, demanding new ways of thinking and new tools for exploration. The story of the cosmos is one of ever-deepening wonder. Each discovery opens new doors, revealing mysteries that challenge our understanding and fuel our imagination. From the smallest quantum fluctuations to the grandest cosmic structures, the universe beckons us to explore further, to ask bigger questions, and to embrace the unknown. The seeds of structure may have been sown in the earliest moments of time, but the narrative they have grown into is far from over. As we gaze into the night sky, we are reminded that the cosmos is not just a collection of facts but a profound story, one we are only beginning to unravel. And perhaps, in the process, we will come to understand not just the universe, but also our place within its vast and intricate tapestry. Problems with Copernicus. Where are we going? It is a question that has intrigued humanity since the dawn of astronomy. The Earth spins on its axis while orbiting the Sun. The Sun, in turn, spirals around the Milky Way, and the galaxy itself moves through space, pulled by unseen forces. But when we zoom out to the grandest scales, the entire Laniakea supercluster, our galactic home, is moving, pulled toward a point in space hundreds of millions of light-years away. This destination, identified in the 1970s through the study of the cosmic microwave background radiation, was dubbed the Great Attractor. Our local group of galaxies, along with countless others, is rushing toward this enigmatic point at an astonishing speed of 1,000 kilometers per second. But what could be there? What gravitational leviathan lies hidden, pulling such vast cosmic structures toward it? The mystery deepened and astronomers realized that the Great Attractor resides behind the zone of avoidance, the central region of our Milky Way obscured by dense clouds of interstellar dust. Observing this region required X-ray telescopes, which revealed the Norma Cluster, a massive congregation of galaxies. Yet, even this cluster could not fully explain the immense gravitational flow. Further investigations showed that the great attractor itself is in motion, pulled toward an even greater structure. This new discovery, the Shapley supercluster, lies 650 million light-years away and contains the mass of nearly 10,000 Milky Ways. It is the largest concentration of mass known within a billion light-years of Earth. But the story didn't end there. In 2017, researchers proposed a counterbalance to Shapley, the dipole repeller, a vast underdense region nearly opposite the Shapley supercluster. While it doesn't literally repel matter, its gravitational weakness allows more massive structures, like Shapley, to dominate the cosmic flow. Together, Shapley and the dipole repeller create a colossal stellar river, a billion light-years wide, through which galaxies, including our own, are swept. Yet, this is only one of the peculiarities revealed by large-scale cosmic mapping. Another enigma challenges the very foundation of our understanding, the axis of evil. The CMBR, a relic of the universe's infancy, is extraordinarily uniform. Its temperature varies by just 1 part in 100,000, a testament to the homogeneity of the early cosmos. However, when scientists divided the CMBR into large segments, they found an inexplicable pattern. The temperature differences between quadrants align with the plane of our solar system. This alignment defies the Copernican principle, which asserts that no position in the universe is special. How could the vast, ancient cosmos possibly be linked to our local solar system? Some, like Charles Bennett of the WMAP telescope, suggest coincidence. Others, like Dominic Schwartz, acknowledge its stubborn persistence, even in data from the Planck telescope. This axis of evil remains a mystery, one that gnaws at the edges of modern cosmology. The CMBR is often called the baby picture of the universe, capturing the moment, 380,000 years after the Big Bang, when photons could finally travel freely. But what came before? How did inflation, a period of exponential expansion in the universe's first fractions of a second, begin? One idea suggests a sea of dense vacuum energy in the primordial universe. A quantum fluctuation could have sparked an inflationary bubble, growing rapidly into a universe. If this is true, there might be other inflationary bubbles, other universes. Perhaps they lie just beyond the CMBR, invisible yet potentially detectable through faint collisions with our own bubble. These collisions could leave imprints, subtle anomalies in the CMBR that scientists are actively searching for. The mere possibility of evidence for a multiverse electrifies the scientific imagination. If we could detect such an imprint, it would revolutionize our understanding of reality itself. Where are we in all of this? From the cosmic to the local, our address reads, Observable Universe, Laniakea Supercluster, Virgo Cluster, Local Group, Milky Way, Orion Arm, Solar System, Earth. Each scale reveals layers of structure and order, shaped by simple yet profound principles: gravity, dominated by dark matter, and expansion, now driven by dark energy. These forces transform chaos into beauty. Galaxies swirl in vast filaments, illuminated by the warm afterglow of the CMBR. The collective work of scientists like Copernicus, Shapley, Zwicky, Rubin, Zeldovich, Peebles, and countless others has brought us this far, revealing the intricate dance of matter and energy across the cosmos. Yet, for all that we know, mysteries remain. What drives dark energy? What is dark matter? And what secrets still lie hidden in the stars? The universe is vast, its story written in light and shadow, its answers scattered across time and space. And as we continue to unravel its mysteries, we are reminded of our place within this grand, unfolding narrative, both observers and participants in the endless exploration of the cosmos.